Hello everyone. So based on the lecture, we are looking at chapter 3. We look at system response, and in the lecture I'm explaining how the operation, the response of a system can be categorized to two main categories: the temporary response, which dies away after some time, and then the steady state response, which stays for longer time. We looked at the spring example, and we looked at one example, first order system, which is the floating limit for the valve for filling up the liquid inside the tank. So we looked at the system point of view, and we looked at how the response varies with time, how the temporary or transient response dies away, and then we have the permanent response or the steady state response. And we looked at the differential equation representing this operation, and also the electrical circuit example that had very similar performance, and with same concept we reached to this generic form that many first order systems are following, and that has this format here. The format here, I'm going to write it down again. Before I move to the section for solving the first order differential equation, I'm just reminding different types of inputs that we might have for our system. So here figure 3.5 is describing 4 different types of input signals that our system can have. So section A is showing this step type input signal, and that is representing a system that has absolutely zero input, and then all of a sudden we have this constant value for the input. That represents the step input signal. And then B is representing the impulse. So we have very sharp peak at one point, and the rest is zero. So you can call that impulse input signal. Another type of input signal that a system can have is called ramp. So we have this constantly increasing line, we call it ramp. So that means that it is increasing continuously, and we have a slope, we can calculate that. So that is also a type of input signal that a system can have. Another type of input signal that a system can have is this oscillating sinusoidal signal. And that is also important to know. All these types of input signals can be considered when we are looking at solving differential equation. Now I am going to move to explain how we can solve a simple first order differential equation. And for this approach here, I'm going to stick to two concepts. I'm going to look at the step input signal, because in many cases that is what is happening. Here, when I'm looking at my circuit, so I don't have any connection, and then all of a sudden I have my input voltage applied to the system. So that can be considered as the step input signal. And for here, you can imagine, think about it. What kind of input signal is given to this system? Is it impulse? Is it a step? Is it sinusoidal? Or is it a ramp? Think about it, and we discuss about that in the class. Now, here I'm going to write that down, and then we think about how we're going to solve this first order differential equation. This is page 81 of our reference book. So based on what we have discussed so far in the class, I think I should make it a little bit brighter. All right. So we have this generic form A1 d theta O respect to time A0 theta O is equal to theta I. So we are looking at I for input and O for output. So this would be general first order differential equation. I'm just writing it down here. So this is like generic form of first order differential equation. Now, in order to solve this differential equation, we are going to have one assumption. We are going to say that our theta O is made out of two parts. Later on, I'm going to explain what are these two parts, but for now, we just assume that it is made out of two components. And if we have that assumption, so these are just two variables, I'm going to have derivative of both sides. So in respect to time, I'm going to have that, and now I can substitute this into my main differential equation. I'm going to write it again. After that substitution, I have A1 and instead of d theta O over dt, I'm writing du plus v over dt, and instead of my theta O, I'm writing u plus v, and it has A0 and then the other side. I'm going to distribute it and rearrange that. So A1 du dt plus A1 dv dt, and then I have A0 u plus A0 v is equal to B0 theta I. Now another rearrangement, I just want to have my u's in one place and my v's in one place to kind of make it similar to the fact that I have here u plus v. That's my purpose. So I can write it A1 du dt plus A0 u plus A1 dv dt plus a0v is equal to b theta I. Now, if I look at this section here, I can kind of separate them together from each other, sorry. So I have two parts. Now, the addition of these two should be whatever I have on the right side. Now I can have this assumption. I'm going to say one of them is equal to 0 and another one is equal to whatever I have on the right side. And for this example, I'm going to say that my a1 dv dt plus a0v is equal to what I have on the right side. So this part here, I'm going to equal it to 0. If I put that equal to 0, so what I have in my second section should be equal to my right side, b0 theta I. I'm going to write that part now. Let's call that single star, and I'm going to call that double star. I write the single star again. So a1 du dt plus a0u is equal to 0. So what does it mean here? So it means that based on this smaller differential equation, this will be a part of my response, which I will have and doesn't depend on my input. So my input is 0. So I don't have any input. No input. So this type of response, which is a part of my total response, can be called transient response. Another name that we call it is free response. So the word free response indicates that there is no input. So it's independent on the input. So it means that no matter what happens to the input, I have that transient response happening to my signal. But this is not the whole response. This is a part of the, the whole response that I will get from the system. Now, so we can look at the other parts. As I explained in the class, transient response is a part of the whole response, but is not all of it. So this response is temporary, and it will die away after some time, and then we have that steady state response. And in this case, we are going to call it forced response. And the reason is because we are going to decide what kind of input we want to give to the system. So we are going to force the system to respond according to the input that we are passing to that system. So again, I am going to write that assumption. The assumption was that we have theta O is equal to U plus V. So far, we learned about the first part. So the first part is the transient or free response of the total response. So I'm going to call it transient response or free response. And the second part, which we are going to look at it in a second, is going to be our forced response. So in order to obtain the transient response, we don't need to know what form of the input signal is passed to our system. The reason because this response is independent of the input signal. Now we need to solve the equation. So we want to obtain what is this u. So I'm going to have another assumption here. I'm going to assume that my u is equal to a e power st. So I'm going to assume that my u looks like this exponential form. Now, when I'm looking at it, if I do derivative of both sides, so I'm going to have du respect to time is equal to, you know that when we are doing derivative for exponential functions, the constant that is being multiplied in the t comes out, and then we have another constant here. So we have a, and then we have the s coming out, and then we have the e repeated. Now we can replace this in the formula that we have here. So I'm going to replace du dt and u here in order to obtain the u. So I'm going to write it again. So it was a1 du dt plus a0u is equal to 0. So this was my free response or transient response. I'm going to replace that, so I will have a1, the amount of that. I'm going to replace that and replace that. So I'm going to use the one that is here and the one that is here. So I have this constant a, which we are going to look at it, what it is. And then we have s exponential of st plus a0 multiplied in u, and u we assume that has this form, and then everything is equal to 0. Let's factor out the exponential and also the constant e, and we see how it looks like. So the constant a and e comes out, we can factor it out, and we are going to have a1 s plus a0 equal to 0. So when two things are multiplied together and they are equal to 0, they both should be 0. They both can be 0. So we have two things from here. We have a est is 0, and we have a1 s plus a0. So that cannot be true because that is our assumption. So that we shouldn't look at that. This part is giving us a good clue, because from here we can obtain that s is equal to minus a0 over 1. So now we have a good answer for s, and now we can put that for obtaining the value for our u. Now the u has this form, and now I know the value of s. By replacing that, my u will look like u is equal to the constant a, and then we have exponential e power minus a0 a1 multiplied in t, and that is nice solution for my u. Now we can look at the second part, but before I move to the second part, I need to explain something. So this part was for the transient response. Transient response is the response that is temporary and dies away. Now, for the forced response, there are many different types of functions that we can assume. So, if we look at, for example, the step input, which we looked at it here. So we are looking at the constant. So we should write the v that we have here is equal to a constant for the step input signal. And for sinusoidal, for example, we should write something that relates to sine and cosine. This is explained in page 82 of our reference book. If we have a polynomial form for our input signal, so we are going to look at coefficients of that polynomial. So the solution will look like something like that. And if we have a ramp, for example, we are going to look at something like theta I is equal to b multiplied in time. So our solution will look like something that has a constant multiplied in t. That will give us a ramp signal solution. So different types of input will decide how to obtain the solution in response to that input signal. That's why we are calling it forced response, because we are forcing the system to respond to that kind of input. Now, for this particular example, I'm going to assume that I have a step. So for the step, I'm going to look at the constant value, because up to a certain point it's 0, and then all of a sudden I have this constant value, which is not ramp, is not oscillating, is a constant value. For that, I'm going to put v is equal to k, and that k is a constant. Now let's see how that looks like. So this time I'm going to look at the double star section of my response, and I'm going to see how I can obtain v in respect to a step input signal. Okay, I'm going to rewrite it again. a1 dv over dt plus a0v, based on our initial assumption, is going to be equal to b0 theta I. Now, if I assume that my v, based on a step input signal will give me v is equal to k, and this k is constant. So you know that when we have a constant, what happens to derivative of that? So derivative of v in respect to time would be 0. Now we can replace this inside the upper one, and then we are going to have, so that will be 0, so A1 will be multiplied in 0 plus A0, the V is K, and then the right side will be. Now from here, my V, which is equal to K, can be obtained, and that will be equal to A0. So that will be my V. Now I can write that in my initial assumption formula, which was theta is equal to U plus V. I obtain the U. That is my U. Now I have the V also, so I'm going to put everything here and rewrite that again. Okay. So my theta O is equal to, how much was U? Exponential of minus plus my V this will be the rewriting this assumption based on obtaining U and V. Now if I want to look at this formula, I want to refer it to what we have here in the book. So we have replaced the U and V in the equation that we had for theta O. Now for solving it from this stage, we need to have some initial condition. So for solving any differential equation, these initial conditions are very important, very necessary. Here in this example, we are assuming that at time of 0, at the very beginning, our theta O is also 0. So that means that at the beginning of the time, we have nothing. Theta O is our output. So that means that we have nothing at time of 0. That is reasonable for such a system, but in some examples, we might have different initial assumption. So in this case, we are calling it boundary. If one example is asking you to solve a differential equation with given boundary, so you should take that into consideration when you want to solve it and obtain the final solution for that system. In this case, we are going to apply that. So by applying theta O is equal to 0 when t is 0, time is 0, so we can put that directly into this equation here, and then from there we can obtain the constant A. and then we replace the constant a again in the same formula here, and then we have a specific solution. So up to here we have a general solution, but after applying our initial conditions or our boundaries or our assumptions, then we can get to our specific solution for that particular problem. I think I shared a couple of YouTube videos that are explaining a very basic form of examples, how generic or general solution for a differential equation differs from specific solutions. I advise everyone to watch those videos because they are very good. Now, let's do this on the paper. So, the initial condition in some example might be a boundary or a different way of saying that these are my force assumptions for the solution. So initial condition is saying that at time of 0 theta O should be also 0. Let's apply that. So theta O is 0. I'm putting this inside this formula here and writing it again. So I have A here, and then my top side here, because of the time, will be 0, and then I have theta I. Now, what happens here? That is equal to 1, right? Number 1. Now, A becomes theta I. And that is the value of A, which we can substitute inside that one here. And then we write it back again. Now my specific solution will be and that will give me my specific solution. So I just replace the constant A because I obtained it based on my initial condition. So this is my specific solution, and that will be my general solution. Okay. Now, if I want to refer that to what's happening inside that system, such a system can be assumed like electrical circuit that we have, the RC circuit that we had, or also where we discuss the spring, the way that the spring is bouncing, any sort of system that has a step input signal, and the output has exponential transient response, which dies away and then kind of gets to this permanent output, which is constant. So any system with that kind of operation will have a very similar solution. And in next video, I explain one example that looks like that. Or maybe I can record it here. Yeah, I think I can record it here. So I'm going to look at this example because it's a very short example. There is no need to record it again. So I'm going to look at this example here, example 2, page 83. So we have electrical system, a resistor in series with the capacitor. This system is the one that is shown here. We want to see how those, the constants, how do they look like in respect to actual example. Okay. So this is example 2, page 83 of reference book. So I'm just reading over the example. An electrical system, resistance in series with a capacitor. So I have my input voltage, and I have my capacitor, and then I have my resistor. This is my resistor and this is my capacitor, and I am assuming that is my output. When subject to a step input of size V is found to give an output of potential difference across the capacitor or VC, which is given by the differential equation, such as this. So previous chapter, we learned how to obtain the voltage, the output voltage corresponding to input voltage. So if I'm going to write it down, but if you have a problem understanding how we get that, we can do Kirchhoff's second law, to write the proportion of the VC for in respect to the input voltage. So RC, derivative of voltage C in respect to time, plus VC is V. Just a reminder how we get that. Kirchhoff's second law. You write from the very left side, you write all the voltages. It will be minus V plus VC plus VR is equal to 0. Or equally, you can write V is equal to VC plus VR. And then we keep the VC because it's our output. And we replace the VR with I, the current, multiplied in R, the resistance. And then we keep the R and we replace the I, the current. And the current can be written as this formula that you have here. C derivative of dVc over dt, because that current is the same current that flows through the capacitor. So the same current is flowing all through them. So you can replace that I with IC, and that will be the formula. And then you get to this differential equation that you have here. Okay. Again, if it is hard for you to understand how that came, how we can write that, go back and look at previous videos or look at the lecture from previous chapter. Now, the question is, the example is asking, what is the solution of differential equation, and what does VC vary with? How does VC vary with time? So that is the question. Let's write it down. How does VC vary with time? Now, if we compare what we have here, this this is our differential equation that we want to solve. We're going to compare that with our generic form. This is the generic form. So if we compare that, okay, I'm just putting them together. So we have first derivative, so we can say that it is first order for sure. So RC is equal to A1. So I'm going to write that down. That is the derivative. So my theta O is kind of here, the voltage across the capacitor, VC. So whatever constant is multiplied in that is going to be equal to my A1. So I'm going to write that down. So A1 is equal to RC. Now, the second part. So my VC is theta O, VC is theta O. So whatever is being multiplied here will be my A0. In this case, A0 is equal to 1. Now on the right side, I'm looking for B0. So in this case, my B0 is also 1. That is 1 and 1. So my B0 is also 1. Okay. Now that I have this information, I can simply substitute them into the solution that I obtained for a typical first order example that we just discussed. So this is my specific solution for similar system. So I can substitute my B0, A0, and A1 to obtain the solution because the performance will be similar. And the reason that we can do that is because in such a system, we have a step voltage V according to the description of the example. We know that that voltage across the capacitor has exponential performance, but that is a transient performance and gradually dies away, and we are going to obtain a constant value across that capacitor over the time gradually. So that is very similar to that generic form that we just discussed. I'm just going to replace this into my specific solution, and that will give me specific solution which includes both of my transient and forced solution. So I write it again just to be sure that everyone understands what I'm doing. Now I replace them here. So B0 is 1, A0 is 1, so I will have exponential of A0 is 0, A1 is RC, so it is and then B0, A0, both of them 1. What I can do from here is I can factor out the theta I. I'm just going to leave it as it is. Now, this will be my theta O. This is the specific solution for that question. Now, here, by comparing my solution with that solution, remember we were putting these guys, comparing them together. Yeah, that was the way we did it. So here, theta O is my voltage across the capacitor. So this is my output in generic form, and this is my output, my desired output in this particular example. So if I replace my theta I with my input, again, my input is my voltage. So if I replace theta O, VC, theta I, V, I can have my VC is equal to minus V exponential of C plus theta I is my V. And that will give me a very nice solution for this problem. I can also factor out the V to have only one of them. So output voltage or potential difference across the capacitor, voltage across capacitor C is equal to, I'm factoring out the V, that is my input, which in this case I'm assuming it is a step input, and then I have 1 minus, and that will be my final solution for this particular example. I hope everyone is understanding it. I'm trying to improve my handwriting, but it's not going anywhere. Okay, so what does it say? So let's look at the performance. Let's look at the performance to make it super duper clear. Now, at time 0, this is my time, this is my output. So at time 0, we have nothing. That will give me 0 here when I put t is equal to 0 in this equation. That will be exponential of 0. It will be 1. 1 minus 1, 0. 0 multiplied in V. My VC will be 0. So I'm starting from 0 here. Now, when t is increasing, t is not 0 anymore, I have this exponential happening, okay? No matter what I have here, I have this gradual exponential happening. So I'm going to have that performance, and it is increasing up to a certain point. Now, how far that t can go? It can be very large. It can be very big number. Let's say infinite. If we have exponential of infinite, what happens to that? Exponential of infinite is equal to, yeah, based on calculus, based on mathematics. So that will be 0. So that will be cancelled out, and then my VC will be equal to my V. So I'm going to have that kind of performance, and that will give me a solution for this problem. I hope it is clear and everyone is understanding what's happening and how we can solve a differential equation, and how useful they are for controlling a system. So when we know how a system is performing, how a system is responding to different kind of signal, then we know what to do with them, how to modify those responses in order to control them. So these are very essential information for your learning. Thank you everyone.